All right, so this is a continuation of section 6.8. Okay, so this is an excellent opportunity to show you what I use this top row for. Basically, I would put up here, this is chapter 6, and this is percent yield and limiting reactants. Maybe and put continued. Whoops. All right, so this is now looking at from the chemical standpoint. So we're actually going to look more at the calculations of how we're going to do this. Okay. So first of all, I wanted to get some of this vocabulary into our notes. Okay, so the first one, the first concept that we want to look at is our limiting reactant. And sometimes this is also called a reagent. And for all of our intents and purposes, we're going to use those interchangeably. Okay, no difference to those. And this is the reactant that's going to limit the reaction. Okay, so this is going to limit how much product we can form. And it's going to be the reactant that's going to be used up first and used up in its entirety. And once it's used up, the reaction stops. Okay, if you run out of butter when you're making cookies, you can't make any more cookies until you get more butter. And so I was referring to the previous video looking at our cookies as our non-chemical example. Now we also introduced with our cookies example the term of excess reactant. Again, or reagent. So these are the reactants that are not your limiting reactants. Okay, they are going to basically be there in excess. They're going to be left over. And then we have our theoretical yield. Our theoretical yield, this is the maximum amount of product that can be formed. Now, that definition, that phrasing is a little tricky, okay, because it's not the maximum of any reactant that we can react to form a product. It's the maximum amount of product that can be formed before we run out of something. Okay, so let me write that down, and then I want to bring back the cookie example to kind of show you how the phrasing of this is a little misleading, and we want to make sure that we get that clear in our head before we start doing calculations. It's the maximum amount of products that can be formed. So what we're looking at is when we talked about our cookie example, okay, so I'm going to scooch this up a little bit, is we looked at how many batches we can make from all the butter, from all the sugar, and from all the flour. Now, if we take this theoretical yield being the maximum amount of product, it's easy to think, well, I can just make 3 batches, right? I have enough sugar and enough flour to make 3 batches. That's the most cookies I can make, so that must be my theoretical yield. Okay? But remember, we determined we can only really make 2 batches, okay? Because we run out of butter first. We don't have enough butter to form 3 batches. So the maximum amount of products that we can make, okay, the maximum amount of cookies that we can make are 2 batches. Okay, so the 4 dozen cookies. So in chemistry, even though we define this as the maximum amount of products that can be formed, okay, this is basically the maximum amount of product that can be formed by completely reacting the limiting reactant. And I shorthand, by the way, limiting reactant LR. So we can put that up there. A lot of times theoretical yield, I may shorthand TY, just because we're going to kind of write that a lot. Now, one thing about theoretical yield, okay, we have the word theoretical here. Anytime that you talk about theoretical in chemistry and science, biology and physics, okay, when you're talking about something that's theoretical, it's not something that's done in a lab. Okay, that's done by calculations. It's done by thought experiments. It's done by putting a piece of or a pen to a paper and doing some calculations. Okay, so our theoretical yield is always calculated. We're always going to have to do some sort of calculation in order to figure out the theoretical yield. Okay. Now that's different than our actual yield. Our actual yield is how much product we actually end up with. Okay? Now that is, when we talk about actual, that means that we have to actually do the experiment. We have to go and measure out the ingredients, perform the experiment, and measure out how much product we end up with. Okay, so when we're talking about an actual yield, this is something that is never calculated. It's never done by a calculation. We have to do the experiment to get this value. Okay, we have to get it via measurement, not via any calculation. Now, because when you guys perform any experiments at home, balances, you don't have at your disposal, so you're not going to be able to really quantify any actual yields. So your actual yields are going to be given to you in a problem. Okay, they're gonna say something like, you know, you could be lucky enough for the question to say it yielded this amount of product. But probably not. It's more likely going to say, you know, 10 grams of ammonia was obtained after performing the experiment or something like that. So for practice problems and whatnot, your actual yield is something that's going to be given to you. Okay. Now the whole point of doing all these calculations is to look at our percent yield. And this is basically looking at the efficiency of the reaction. Also sometimes used as looking at the efficiency of the chemist. Little test for that. Okay. And we calculate the percent yield by taking our actual yield divided by the theoretical times by 100. Now this is an equation that you are definitely going to want to know. Okay? In other words, have this memorized, have this in your memory bank. So you may want to, because you have access to your notes during exams. For the online ones, you know, have this on a sheet of paper maybe. But keep in mind that once you take the cumulative final, that's a paper version, so you'll need to know this equation. Okay, I can guarantee on the exam, on your homework quiz, and on the final exam, there is going to be a question dealing with limiting reactants, theoretical yields, actual yields, and percent yields. Okay, that is a guarantee. All right. So let's now talk about these calculations that we're going to be doing. Okay, we are not going to be calculating actual yield, okay, but usually our goal is always going to be percent yield. In order to figure out percent yield, we have to know the theoretical yield, and in order to know the theoretical yield, we have to know what our limiting reactant is. So first off, what I want to talk about in this video is determining, okay, figuring out how to do the calculation to determine your limiting reactant. So the general pathway that we're going to be taking to calculate our limiting reactant is we're going to take one of our reactants, okay, however many we start with of that, and we want to convert that, we want to calculate, okay, using our railroad system to determine how much product we can form if we completely react that reactant. Okay, and when we look at limiting reactants, we are going to do two calculations always. Okay, because you're going to have two reactants, possibly more, okay, but usually just two. So we're going to have to figure out how much product can be reacted by doing the first reactant, and then how much product we can form looking at the second reactant. Okay, so much like we did with the cookies, figured out how many batches we can make from all the butter, how many batches from the sugar, how many batches from the flour, and looked at how many cookies can we actually make. Okay. The general pathway that we're going to follow, okay, this we're going to be basically doing the same types of calculations over and over, okay, is we're going to start with grams of A, so grams of one of our reactants. We are wanting to convert it to some of our product, and usually it's easiest to look at grams of your product. So if we want to change to something else, okay, eventually we want to end up with, say, grams of B, Remember, if we're going to change from one compound to another, the only way that we can do that is to use stoichiometry. So we're going to have to get from grams of A to moles of A. And then we can use stoichiometry to go from moles of A to moles of B. And then from moles of B to grams of B. And that's the general pathway that we're going to take. And we're going to take it over and over. We're going to do a lot of these calculations. Okay. So our conversion factor to get from grams of A to moles of A, this is our molar mass. And where do we get our molar mass? We get our molar mass from our periodic table. Right, we add up all of our individual molar masses of the atoms. Then we have moles of A going to moles of B. Okay. That is our stoichiometry step. Okay. Also known, your book calls it the mole to mole factors. And where do we find this conversion factor? We find that on our coefficients, right, of our balanced chemical equation. And then our last step, again, this is molar mass. And again, we're going to find that on the periodic table. So we're going to be doing this a lot. Grams of A, you're going to hear me say it a lot on these videos. Grams of A to moles of A to moles of B to grams of B. So let's look at an example. And again, this is an example of finding the limiting reactant. Remember, we're going to build on these concepts in each of the videos. So let's look at this balanced chemical equation. It says calcium carbide. And we're going to combine that with water. And we're going to form calcium hydroxide. And C2H2. Don't worry about the name of that. That's an organic molecule, and we don't require you to know those names. So let's start off kind of simply here. Okay, let's kind of cut off the grams and just deal with going from moles of A to moles of B. And let's ask ourselves, what is the limiting reactant when we have 1 mole of each of these reacting? So if we have 1 mole of each of those, okay, which reactant is going to run out first? Is the calcium carbide going to run out first, or is the water going to run out first? Okay, if you have your answer, that's good. If you don't have your answer, look at it this way. Okay, remember we can break this into two parts. So if we have 1 mole of calcium carbide, okay, and we completely react that, how many moles of water do you need? Well, you need 2. Do you have 2 moles of water? No, we only have 1 mole. So in order to completely react all of this calcium carbide, we actually don't have enough water. Okay? So the water is going to run out first. Now we can also look at this as how much product we're going to end up with. Okay? And that's the way that I want to show you how the calculations are done so that we can apply this full length calculation here. Okay? So remember, we're going to do 2 calculations. Okay? One of the calculations is going to start with our 1 mole of water. Our other calculation is going to start with the 1 mole of calcium carbide. Now we want to compare a product, and we want to look at how much can we form. And that's the whole idea, is we're trying to get to a theoretical yield. How much product should we end up with? So for the first calculation, I want to convert from moles of H2, okay, so I'm at moles of A, and I want to convert to moles of B. Okay, it doesn't matter where we convert to. Doesn't matter if we choose calcium hydroxide. Doesn't matter if we choose C2H2. Okay? It doesn't matter as long as we choose the same product to look at down here. Okay? So I'm going to choose, let's look at calcium hydroxide. Let's choose the compound we know how to name. So this is our stoichiometry step. So I'm going to use my coefficients. I have my balanced chemical equation. My coefficient for water is 2. So I stick a 2 there. My coefficient in front of calcium hydroxide is a 1. So we end up with 1 divided by 2. We have 0.5 moles of calcium hydroxide. Now we want to do similar calculation here, except we're starting with moles of calcium carbide. So we have to put moles of calcium carbide in the denominator. Then we want to choose the same product to compare. Always want to choose the same product so that we can compare them directly to each other. Again, use our coefficients. The coefficient in front of calcium carbide is 1. And coefficient in front of calcium hydroxide, still 1. So we'll end up with 1 mole of calcium hydroxide. So if we completely react 1 mole of water, we will end up with 0.5 moles of calcium hydroxide. If we are able to completely react 1 mole of calcium carbide, we will end up with 1 mole of calcium hydroxide. So what is the maximum amount of product that we can form? The maximum amount of product that we can form is this 0.5 moles of calcium hydroxide. Okay, because remember, we're going to run out of water, so we can't form that full 1 mole of calcium hydroxide. Okay, so this is the maximum amount of product. That's our maximum product, which means that this 0.5 moles of calcium hydroxide, this is our theoretical yield. And that makes, I'll choose a different color here. That makes our 1 mole of water, H2O, is the limiting reactant. And the water limits how much product we can form. All right. Let's do another example, and let's utilize now our full calculation road here. We're going to start with grams of A and end up with grams of B. So what is the limiting reactant when 100 decimal grams of H2O reacts with 100 decimal grams of calcium carbide? Now it's really tempting to look at this and go, hey, I have the same grams of each of my starting compounds. I had the same amount of moles up in this question, so it must be water that's my limiting reactant. Now we can't do that with grams. Okay? The only way that you can compare one compound to another is to compare moles. Okay? So when we have a mass here, we can't tell anything from just comparing 100 grams of water to 100 grams of calcium carbide. Okay? Whenever we start with mass, you have to do a calculation. You can't look at that like we did up in this first example. Okay? So we're going to have to do these two calculations. Okay? And we're going to follow this general pathway. We're going to do the two calculations. One calculation will be with the 100 grams of water. Okay? We'll start with 100 grams of water, convert it to moles of water, then moles of, we'll stick with calcium hydroxide, and then 2 grams of calcium hydroxide. Okay, that's one calculation. Then the second calculation, we're going to start with our 100 grams of calcium carbide. So that'll be our grams of A. Then we'll convert the 100 grams of calcium carbide to moles of calcium carbide, then to moles of the same product that we did for the previous calculation, okay, with the water. So moles of calcium carbide to moles of calcium hydroxide, and then to grams of calcium hydroxide. Then we can compare the grams of calcium hydroxide from both calculations to figure out what's our maximum product, in other words, what's our theoretical yield, and then therefore that will show us what our limiting reactant is. So let's look at those two calculations. So we're going to start with 100 grams of water. We're going to do a long railroad. And then we're also going to do a second calculation with our 100 grams of calcium carbide. And why is that decimal important for us at the end of 100 grams? That decimal is important because it dictates how many sig figs we have. Okay, with that decimal there, it makes all 3 of these values significant. Without a decimal, it just makes the 1 significant. All right, so we have grams of water. We want to go from grams of water to moles of water. And that's that grams of A to moles of A step. And we want to use our molar mass for that, so we need to look up our values in the periodic table. So we can look those up. And I'll show us on the calculator. We have 2 hydrogens, and each hydrogen is 1.008. Then we have 1 oxygen, which is 16. So we have 18.016 grams per mole. Now remember, when we do molar mass, that is always per 1 mole. Okay, it has nothing to do with our coefficients up there. Molar mass is the mass of 1 mole. Okay, so our 1 always goes with our molar mass. Next step, okay, we're at moles of A now. Oops. We want to go from moles of A to moles of B. So we're going to use our stoichiometry, okay, and that's where the coefficients come into play. So we're at moles of water, so we're going to put moles of water in the denominator so those units cancel. We decided we were going to stick with calcium hydroxide, so we're going to go to moles of calcium hydroxide. Then we use our coefficients. Okay, so our coefficient for water is 2. Coefficient for calcium hydroxide is 1. And then we're ready for our last calculation, or last step in this calculation. We want to go from moles of calcium hydroxide to grams of calcium hydroxide. So we're going to use molar mass for that. Again, we're going to consult the periodic table. So we're going to go moles of calcium hydroxide. And we're going to convert this to grams of calcium hydroxide. All right. So we look up in our periodic table. Calcium is over in group 2A, okay, the 4th period. It has a molar mass of 40.08. We have another hydrogen, 1.008, and our oxygen, oops, over here, group 6A, group 6A at 16.00. So to calculate the molar mass of our calcium hydroxide, we take our 40.08 for the calcium. Then we have 2 oxygens and 2 hydrogens. So we're going to add that of 2 times 16, and then 2 times 1.008 for a molar mass of calcium hydroxide of 74.096 grams per how many moles? Per 1 mole. Molar mass is always per 1 mole. All right. So we have our 100 grams of water. I'm going to multiply by 1, divide by 18.016. Again, multiply by 1, same thing. Divide by 2. Then multiply by 74.096. Divide by 1. And if we completely react 100 grams of water, okay, theoretically we should end up with we have 205.6394. We had 3 sig figs to start with, so we're going to end up with 206 grams of calcium hydroxide. I had to round up that 5 because we had a 6 to the right of it. All right, try out the next calculation, okay, following the same pattern, grams of A to moles of A to moles of B to grams of B, okay, and remember we're going to convert to this grams of calcium hydroxide again. So go ahead and pause the video. Once you've taken a stab at it, I'll work out that calculation when you unpause the video. All right, 100 grams of calcium carbide. We want to go from grams of calcium carbide to moles of calcium carbide. And that's our molar mass, so we're going to consult our periodic table. Calcium has 40.08 of a molar mass. Carbon has 12.01. So we have 40.08 plus 12.01 times 2. So we have 2 carbons there. So I have 64.10 per 1 mole. And then we want to go from moles of calcium carbide to moles of calcium hydroxide. Remember, we want to stick with the same product that we chose for the first calculation. Then we look to our coefficients for that ratio. It's a 1-to-1. And then our final step is just like the final step up above. Okay, we're wanting to convert from moles of calcium hydroxide to grams of calcium hydroxide. And we still have 74.096 grams per 1 mole. So we have 100 divided by 64.10. Then we have 1s here, so they're not going to change our calculation. We're going to multiply by 74.096. Calculator gives us 115.59. We need 3 sig figs, so I'm going to have to round that 5 up. So I get 116 grams of calcium hydroxide. So now we go back to answering our question. We're trying to figure out what is the limiting reactant here. Okay, so the maximum amount of product that we can form is the 160 grams of calcium hydroxide. Okay, because we run out of the calcium carbide and we won't be able to make that full 206. Okay. Remember the cookies, once you run out of an ingredient, you're done. You can't make any more cookies. So in this case, our 116 grams of calcium hydroxide, okay, this is our maximum amount of product. So this is our theoretical yield, which makes the 100 grams of calcium carbide our limiting reactant.